Okay, welcome everyone. Thanks for tuning in here today. And during this session, we're going to talk about just some of the complexities of deploying and managing production workloads in Kubernetes. But we're going to approach it from the easy way perspective. And by the end of this, hopefully, you'll gain some insight, and we will provide you a boilerplate on how to deploy your telecom infrastructure into Kubernetes in an easier way. There's lots of components that, as you're aware, need to take place and need to exist in a telecommunications environment. And we're just going to kind of dive right into that, show you what we've done and how we've been able to accomplish it, and then show you just all of our manifest, our kind of open source a lot of that for you in order to help you kind of migrate your workloads into a Kubernetes environment. So let's get started. I'm Joe Mordica. I am the founder of Voxo, and I'm a Christ follower, a husband, father, family guy. I enjoy technology. I enjoy building technology companies. I enjoy solving problems for people. I enjoyed finding ways to monetize products and help people communicate better as far as being able to innovate in the telecom industry. So it's a lot of fun for me, and just always trying to challenge the status quo. Here's some contact information for me, and then obviously all of this, everything that went into this. Special thanks to my team. Fred Posner with LOD, good Kamailio resource. Sean McCord, great Kubernetes expert that kind of helped us consolidate our environment into a Kubernetes friendly way. Yufui Teo is another great Kamailio resource that did some consulting for us related to RTP engine and how that works. So we're going to tie all that together and show you how we've deployed our infrastructure and what that means here in just a second. So why Voxo? Voxo is a telecommunications company. We're a software company. We build, deploy, and manage our own software stack, and we use all open source tools that we can. We use Asterisk, we use Kamailio, we use RTP engine, we use MySQL, we use all the tools that you're probably using in your environment. Voxo exists to fix a lot of the problems in the telecom industry. There's so many broken things in the telecom industry, from billing to support to outdated systems. And we want to provide people a way out of that and show people that business can be done differently, and business can it should be built on relationships versus like contracts and transactions. So we don't require any transactions. We have one-page bills. We don't make people do any phone leases. We're constantly adding on to our telephony solution, with WebRTC functionality, CRM integrations, queue management, contact center related features. We listen to our customers. We want to make those changes and innovations for them as we continue to build out our product and create the future of communications. So we're just going to kind of dive right into the meat of the presentation here, and we're going to go through this kind of component or network diagram that, and I'm going to explain some of these components. And you're probably familiar with a lot of them as you run them in your own environment. But I just want to show you what we're about to create in a small demo with just 1 or 2 easy steps and 5 or 10 minutes. So I'm going to go ahead and share this interactive diagram. And by the way, everyone has access to this via our GitHub repo that I'm going to share at the end of this meeting. And so you'll be able to see all of this. You'll be able to click around here and see how all these components interact with one another and stuff like that. So just real quick as an overview here, you can see some of the components that we're using here. RTP engine, Kamaili. And then asterisk on the LAN. And I'll talk about some of these things here in just a second, but as an overview, these 3 boxes represent 3 completely different data centers and clusters across GKE, across Google Kubernetes engine. So this all uses Google's VPC, global VPC. So all of these components between these regions can communicate with one another out of the box. Any one of these 2 regions can completely fail, and this region, let's say, picks up all the traffic. There's redundancy in every component within this infrastructure. Everything uses and is highly reliant on GKE's multi-cluster service and GKE multi-cluster ingress. And I'll talk about that a little bit, but that's kind of the GKE multi-cluster service is really kind of the magic sauce that connects all of these services together and does some service discovery things that like Istio would be way too bloated to implement here. And that's one reason we're using GKE is because of the way that they implement this service discovery method. So everything is monitored with Prometheus using Google Cloud Monitoring, Stackdriver exporters, and then we use Google Cloud logging to log all the events in this stack. We use Constellex for DNS SRV and Geobased DNS SRV. So for like legacy SIP clients that need to register to our infrastructure, Constellex will determine the closest region to that user within proximity and have them register to the Kamailio instance that's closest to them in proximity. We used BigQuery for storing like long-term storage CDRs. It's great for that. It's great for data analytics. We use Amazon S3 for storing, recordings, media files, any assets and things like that. A lot of our the way that all of our services communicate with one another is via NATs. NATs is a messaging queue and handles all of the messages that need to get to and from different services. So each NATs implementation is a 3-node cluster in each data center. And NATs is able to communicate via superclusters to one another. It sounds really complicated. It sounds like there's a whole lot of setup, but it's literally just one YAML manifest, Kubernetes manifest that gets deployed, and using multi-cluster service with GKE, we're able to deploy that with just one simple YAML. I'll kind of try to get into a little bit of that during the call, or during the demo. But as you can see here, external providers, your upstream carriers, would interface and connect directly to each Kamailio instance in each cluster. The only requirement in all of this, by the way, is run in GKE. Every bit of it is run. There's nothing running on like just regular virtual machines. Everything is managed in GKE clusters. The only caveat is that you'll need external node pools for things like Kamailio and RTP engine, since we need to allow NAT to happen and allow ports to be open for communicating with legacy SIP clients. If it wasn't for legacy SIP clients, you wouldn't have to have that external IP assigned to Kamailio and RTP engine for RTP and SIP registrations. But everyone still has desk phones for the most part, and so we have to deal with that. Each one of these services, So Camellia, RTP Engine, Asterisk, they all have sidecars, and these sidecar apps are kind of like helpers to each primary component. And those helpers help transfer messages to and from other services within the platform to be able to handle, whatever RTP Engine and Camellia need to be aware of. RTP Engine handles the bridging of the media to all of the Asterisk servers. So Asterisk remains on the local network and doesn't gain access to the public IP space. RTP Engine does, and RTP Engine handles the media relay from the SIP client or WebRTC user to Asterisk. RTP Engine is also set up to act as a media relay, so it can do SIP UDP to WebRTC, and it just receives commands from Camellia and does any kind of relaying of the media there. It handles proxying all media, whether it's WebRTC or traditional UDP. So that said, everything in the cluster relies on Vitess. Vitess is the backend MySQL orchestrator tool, if you will. It's extremely scalable. YouTube uses it. It was originally a YouTube project. It's self-healing with the Vitess operator in the Kubernetes environment. It runs on single master. It has multi-region support. So each region has its own kind of cluster and is able to communicate with each other via etcd cluster and a global lock server. There's multiple instances per region, and you can delete, specific regions, bring them back up. They download the latest backup and sync themselves to the rest of the cluster. It's really awesome to be able to work with. We have a Kube client instance, and it handles the distribution of external IPs to RTP Engine and Camellia. The Kube client will assign those static IPs to RTP Engine and Camellia when a new VM is spun up. So because our customers need our IPs added to their firewall, we have to kind of reserve external static IPs in GCP, and the Kube client just grabs an available one, assigns it to Camellia and RTP Engine instances, and basically adds them to the cluster. So it handles all that automatically and kind of watches those node pool nodes. So this is just a basic overview of the different components that are being used here, how they're being used. I don't think I went over Camellia, but it basically handles any SIP registrations, WebSocket connections, DMQ for user location presence, HTable replication. It handles presence as a presence server as well. It dispatches all of the requests and load balances them to any Asterisk server in any cluster. So when Camellia gets a request, it can distribute that request to any Asterisk server within these three clusters, and because it's aware of everyone. Now it's going to prioritize the local Asterisk instances within itself, but it's capable of going cross-region and going over GCP's internal network. And then of course we have Asterisk. Asterisk is set up to handle media, things like parking, queuing, IVRs, that kind of thing. We connect via ODBC to Vitess. We use Fast AGI. We use AMI for presence notifications to Camellia. So anytime a device goes off hook or or is being utilized. A presence event is sent to the Camellia sidecar, and then gets dispatched to the SIP to the necessary SIP clients. Each Asterisk server in each region can connect to and communicate with any other Asterisk server in any other region. So let's say there's a call parked on another Asterisk server in another region. Well, it's going to do the lookup in Vitess and /MySQL, know which Asterisk server that parked call is on, and it will take care of bridging that call to another Asterisk server in another region. So everything that you see here is a single is thought of as a single cluster. It's all active. There's no kind of failover in place other than any cluster can survive each other. Just the last kind of component here, the thing that kind of ties everything together from a web user perspective, from a WebRTC perspective, is Google's GCP Global HTTPS Load Balancer. This handles any HTTPS traffic coming in, whether it's WebRTC, whether it's WebSockets, whether it's just regular HTTP traffic. And we can use this one global load balancer to distribute requests amongst all of our regions and clusters. So this global load balancer has multi-cluster support, has multi-region support. It's a single IP for you to point your domain to. It routes to any API instance and any region. It always keeps up with the health of each API instance. It keeps up with the health of each Camellia instance. It's always pinging that WebRTC port to make sure that it's alive and well. And if it's not, it takes it out of the equation so that it doesn't send that Camellia instance any more WebRTC requests. It has path-based routing, so we can even do things like phone provisioning and other regular, standard HTTP requests. So that's the really nice thing about using Google's GKE or Google's GCP global load balancer. We have one IP for everything, and those requests can be distributed really any way you want to between all of your clusters. So there's a lot of meat here. And I'm just this is going to be available for you to click around on and kind of see what all of these components do, how they work. And then we're going to kind of dive right back into the presentation and just talk about some key benefits. And hopefully this works. Yeah, so I'm going to kind of make my way through here, and we'll get back to the point in the presentation. Okay. Come on. Okay, so let's look at some reasons that we chose the things that we chose. And by the way, we migrated from a legacy environment on bare metal servers, running in our own co-located data centers, and kind of right into a GKE environment. So so these are the big three for us. We wanted something simple to deploy. So let's say worst case happens, we lose everything. We want to be able to click a button or run a command and deploy everything within 10 to 15 minutes. All three clusters, even add more clusters. And then that's database recoveries, that's external IP registrations, that's everything. And be back up and running in a very short period of time. We wanted something manageable that our engineers can manage, our ops teams can manage, and obviously scalable. In the telecom industry, you know that it has to scale. Every single feature that you build, everything new that you add has to scale. This model is a very scalable model. And we wanted to get away from having to manage servers and services. So in the Kubernetes world, you treat your servers and your services kind of like cattle versus pets. Whereas in the bare metal world, you kind of treat your servers and your services like pets. Like they all have their own, IP schema. They all have their own server host names, and what services reside on each server. Well, in a Kubernetes environment, you don't care, and you shouldn't care. You should just be able to deploy your services. And all Kubernetes does is always try to get to the state that you tell it you want to achieve. So if a service is not running, or if an application is not running, Kubernetes will always try and start that service up for you. It'll always try to restore that service to its desired state that you specify in the YAML. The reason we chose Google is because we believe Google has the best K8s implementation. It seems to be better than AWS and Azure in regards to native service discovery. So it avoids us having to use things like Istio and Cilium, and there's a few others, but we wanted something where we could deploy a YAML file and it would automatically discover services in other clusters, other regions, and connect to those clusters and start chatting. GKE has a really good multi-cluster service implementation, and it's all domain, it's all DNS based. And that's all in our YAML files that I'll show you. That's all in our GitHub repo that is open source, and I'll share the link with that here in a little bit. So obviously we use GKE multi-cluster service a lot. Anytime a component needs to chat with another component or service in another cluster, multi-cluster service is used. So we don't rely on IP connections, because IPs change frequently in Kubernetes, and that's the way that it should be. We use a single multi-cluster ingress load balancer for WebRTC and WebSocket and HTTP, like traditional HTTPS, things like that. So we don't have to. We no longer have like to set up multiple Nginx instances for different types of services, or manage our own load balancer. The nice thing about using multi-cluster ingress is that Google handles the health checks of all of the services that the load balancer needs to connect to automatically. So all of the services are monitored in real time in each cluster, and you can connect the multi-cluster ingress to really any service and any cluster, and the services survive. If they're taken down, they're marked as unhealthy if they're taken down. It's really a fault-tolerant solution, and allows us to have one ingress point where clients can connect to, instead of having like a region-specific IPs and DNS records that fail over to one another. It's kind of a mess, but this really simplifies it. I talked about earlier that we use Constellix for DNS. So very simply, Constellix supports Geobased DNS SRV. So in the hosted telephony industry, you guys are probably using DNS SRV records, putting them in your phones, and then they're reaching out to your servers. So in case your servers change, your IPs change, you can just change your DNS record and not have to mess with the phones themselves or the endpoints connecting. What's nice about Geo-based DNS SRV is that if I'm requesting a DNS SRV record as a phone in Atlanta, and I have a cluster in US East and a cluster in US West, Constellix will return the SRV record that's closest with, from a latency perspective to my SIP client. And that's a really nice thing about using DNS SRV. It'll also include all of the other DNS SRV records within that scope. So you can get to the closest region, but you can also fail over to further regions. One thing to keep in mind is all regions are active. All 3 regions are active and can survive complete outages and maintenance in single regions. So let's say we needed to do Kubernetes updates in US East 4. Well, we could completely dry up that region, dry up all the WebRTC traffic, dry up all of the SIP traffic. Google's load balancers would remove that traffic and dry it up for us. And then we can do maintenance. We can take down database servers. We can take down any component within that region that we want to. And the other 2 regions will continue to distribute the traffic, bring the region back online after the maintenance, and then Google handles the healthy probes of the services that we bring back up. All of this as well is using GCP's managed auto SSL. So, and this is all in the script, the deploy script. So you can specify domains that you want Google to manage the SSL for. So your API endpoints, your anything that's HTTP, HTTPS can rely on Google's managed SSL now. That's somewhat of a new feature. In the Kubernetes environment, there's 2 node pools. One is an external node pool that handles SIP /UDP, like RTP traffic, and there's firewall rules that are in the deploy script that get added to GCP automatically. Those are tagged rules. And then there's a second node pool, which is like a default node pool, and that's everything else in the cluster. So Asterisk, MySQL instances, NATs, Redis, everything that gets deployed on this kind of default node pool. The only things that exist in the external node pool is Kamailio and RTP Engine. Those are the only 2 things that need access to the public internet. And those are the only 2 things that need public IPs assigned. Everything else is inaccessible from the public. And that's just because we need to support legacy SIP clients. That's because we need to support RTP relaying. We need that public IP in order to relay RTP from the client. There's a script and a demo that I'm going to show you in just a minute that we're going to just deploy all 3 clusters. And I'm going to kind of speed the demo up so for the sake of time. But the script is available to you as well as like a boilerplate to kind of get you going. And it's going to deploy everything that you've seen so far. All of the kind of magic and everything that you saw in the previous interactive diagram is all just in a handful of YAML files. Each cluster has their own cluster specific config, and then all the other manifests within the GitHub repo that I'm going to share, it gets deployed to every region. So let's do a quick deployment. I'm just going to kind of talk through this a little bit as we go through it. And then we'll do questions after this and be done. So real quick, what we're about to do is deploy a 3-region production cluster with SSL, with load balancers, with our 2 node pools, with Asterisk, Kamailio, with RTP Engine, with databases that restore from the last known backup. This is with nothing whatsoever created. This is creating firewall roles for us. This is creating any external IPs. This is assigning external IPs. And all of these manifests are going to be available for you to deploy in your own environment. Obviously, some of the images are closed source, but we're okay open sourcing some of that stuff based on request and sharing what we have. I mean, this is how we all get better. So we're going to deploy a 3-node cluster. We're going to specify fresh install. There's a few other command line options that we can use here to just add a cluster if we want and things like that. I'm just going to kind of run through it here. We're deploying firewall rules. We're now deploying the first region in US Central, and it's going through the process of deploying that region. And right here, I'm just showing you the actual create cluster command that gets run on GCP to generate the cluster. So now you can see it being created here, US East, US Central 1. So this is getting deployed, and this is gonna continue on here. What we've been talking about, and you'll be able to deploy this yourself, or use it as a boilerplate for your environment. We're just waiting on this command to finish. So it's deploying the US East cluster. Multi-cluster services and allow Google to register these clusters in what's called a membership hub. And this membership hub is where all of the clusters connect to. Prometheus, RTP engine, some of our other components here. Asterisk is deployed. We have 2 pods up and running here. So I'm just going to kind of skip down the line here. Now we're deploying a completely new cluster. So this first US Central 1 cluster is fully operational, and there are services in this US Central cluster that's looking for services in the other 2 clusters that we're about to deploy. So while the services are up and running, they're still trying to reach out to the other clusters to see if those similar services are alive, so that the services can create their own cluster. So US East 1 is currently deploying. We have some deployments happening here. So now you can see that US East is completely deployed, and now we're deploying US East 4, which is our 3rd cluster. We can see that we have 3 nodes in US Central 1, 3 nodes here, 12 CPUs total. GKE and Kubernetes Kubernetes specifically will use these CPUs as they need to deploy different workloads. Auto scaling is set up so that if the resources start to run low on one of the nodes, Kubernetes will take care of spinning up an extra VM. It will add it to the node pool and start deploying some of those workloads to that node pool, or to that new VM. and we have different CPU thresholds in here. So let's say during the middle of the day when there's lots of telephony traffic, lots of calls happening, that kind of thing, Kubernetes will add more virtual machines to specific clusters depending on the CPU usage and memory utilization. And then at night, whenever the traffic kind of falls off and there's fewer calls happening and fewer activity, Kubernetes will handle the decommissioning of those VMs and bring it back to our kind of lowest state of 3 minimal nodes in each cluster. So we're not paying for extra virtual machines that we don't need and things like that, and we can rely on Kubernetes to accurately handle spinning up and tearing down of those virtual machines, which is really the exactly the purpose of implementing a telephony environment in a Kubernetes environment, where you get to take advantage of some of those auto scaling features. So we have some workloads spinning up here in our last cluster, and yep, looks like everything is deployed. So now we have 3 working clusters. We have a load balancer here that's created for us automatically, an HTTP ingress load balancer. It has things like WebRTC paths, socket IO paths for WebSockets, regular paths here. So if I wanted to, I could resolve to one of these paths, and it would pull up the correct service, and we can see that our services are healthy right here. So we can see that in each data center and in each environment, the GCP load balancer is always sending pings or probes to each service in each cluster. And you can see that each service is reachable in each cluster. So now the load balancer is aware of all of the services in each cluster. It can ping them. It can take them down if they're unhealthy, or it won't actually, the load balancer won't take them down. The load balancer will just remove them. It'll just dry up that service in that particular cluster if there's an issue with it. And then when Kubernetes spins that instance back up, the load balancer probe will add it back to the load balancer so that it can receive traffic. So yeah, that's what we have here. We just went to the URL, Kube API. This is the URL. We have SSL. We have, we're automatic HTTPS. This is our API endpoint. This is just a splash page here that shows to just a live or dead page, basically. So that's the demo. I'm going to leave the link to the GitHub page with all of this content on it right here, and then just go to questions. So let me share my screen. All right. So this is the URL here. You can get there by voxo.co/K8s, and we'll go to questions. Thank you guys for listening, and chat us, speak up if you have any questions. Reach out to us after this if you'd like to get access to some of our resources, some of the things you may not see here that you may want access to. We're willing to share as much as we can and open source as much of this as possible. So now we'll go to questions.